Hello, everybody. Today we will build a model that will count number of cell colonies present in the pictures. So we will be using Deepchem and Keras for this project. So make sure in my Conda environment, I have TensorFlow, Keras, Deepchem, and all those things. So make sure you have them with it. And then we also be using this datasets from Broad Institute. So you're going to download this zip file and make sure you unzip it and have it in the same folder as your cell count Jupyter notebook is in there. So this has a bunch of pictures, 19,200 to be precise, with the cell colonies, and it has labeled in the file name. So we can extract the labels as well. So let's jump right into it. So obviously we are using Jupyter Notebook. You can do this in Google Colab as well. So let's begin. So let's start with, let's import Deepchem, import NumPys, and then import OS so that we will be able to read, and then regular expressions that will help us extract the label from our file name. So once that is done, let's create directory. So we're gonna have our data. So this is the folder that has all those images, version 1 images, and then let's create an empty list called files and an empty list called labels, so that we're gonna attach all the files and labels so that we can train it. Okay, so let's create a for loop. So what we are going to do is we're going to go into this folder and read one file at a time and extract the label from the file name as well. Okay, so for f in os.list directory, and we're going to go to our directory. And then if f dot ends with .tif, so the file name is going to end with .tif. So if it ends with .tif, then we're going to attach that files to our empty list, files.append. And I'm going to add a bunch of things in there, but I'll get back to it. Then we have labels.append as well. So we're going to add in our files.append os.path .join. So we're going to join all the files. And what are we going to join? We're going to join our directory, and we're going to join our file F. And same goes here, but this time we're going to use the regular expressions. So it's going to find all. And what we are trying to find here is the, let me write it out. So the file names are gonna be written like this: C13. So let's say whatever number that comes after C is the number of cell colonies, and this has been labeled by humans. So this 13 is what we are trying to extract. So this would be our Y variable, if you think that way. So we have 13 colonies. Okay, so what this regular expression will do is it's going to read the file and extract this 13. So let's do it. So re.find all. So what we are trying to find here is a pattern that .c, and what comes after that C, and that's going to be, so in this case, it's going to be dot star question mark. So what we are trying to do is what comes after C, but before this underscore. Okay. And we're going to look into F, and then we're going to take the index 0 of it. Okay, so this is going to be a string. So let's convert this into an integers. So we can convert this into an integers. Okay, so these are the file names. Okay, so that's pretty much good to go. Hopefully I won't encounter, let's see, I close all the bracket. Okay, so that looks good. Okay, so I think we are good. So let's read our data sets. So our data sets would be deepchem.data. So Deepchem has this data module that would package these type of data so that it can be easily used with our Deepchem models. Okay, so image data sets. So in this case, we're gonna have files, and let's convert our labels into an array, mp.array labels. Okay, so I think it should, okay, it looks good. There is no error. So let's split our data sets into train and test and valid. So let's call splitter. Let's define splitter. And we're going to be using random splitter from Deepchem. And let's call it train ds, valid ds, test ds. And then this would be splitter dot train valid test split, and we're gonna be splitting our data sets. And you can put seed any number you want if you want to optimize, if you want to do hyperparameter training. 420, I'm putting 420 there. So this should good. Okay. Now let's look at our train datasets.x.shape. So, and then we're gonna look at train. Let's do, it'll take a couple of seconds. Train test ds.x.shape as well. It will take, because it's going through every files to figure out the shape, so it takes a couple of minutes. Okay, so we have 15,360 data image file in our training set, and each picture is made up of 520 pixels by 696 pixels, and the same goes with test. So you can have the y variables as well. So if you want to look at it, you can check for yourself. So that's how you can get the x or y variables. You can change this to y if you want to. And you can see it has only 1920 number in there. Those are the labels, how many colonies we have. Okay, so now we are ready to build our model. So first we're gonna build a Keras image, Keras convolution neural network. Dang it, this is a hard word to pronounce for me. Okay, so we're gonna use convolutional neural network from Keras, and then we will wrap that neural network in a Deepchem model, and then we will predict. Then we use our data sets. So let's try to do this. So from Keras.models, let's import model. From Keras.layers, we need input layers, we need convolutional neural network. Then I'm gonna be using activation function leaky value. I'm gonna be using batch normalizations. Then I'll be using flatten. Then I'll be using dense, dropout. I think these are all I'll be using. So let's start building our model. Let's call the first layer as input layer is input. So we gotta provide a shape to it. So the shape is the pixel, 520 times 696. 520 and 696. Okay, let's call this x as, let's call this input layer as x so that we can reuse this. So now what I'm gonna do is for instead of, we could do a couple of things here. We can do a for loop and do multiple, but let's keep it simple. So let's build x equal to convolutional con1d layers and add filters. Again, this is up to you how many you want to add, 32. And then next thing we're gonna add is kernel. What kernel size we want. So 3. So now what happened, this kernel size is it's gonna read a because it's a 2-dimensional pictures, 520 by 696, it's gonna read 3 pixel on the top and 3 pixel on the vertical. So you have 9 pixel. That's one way to look at it. In a cube, like imagine a cube of 3 pixel on the width, 3 pixel on the lengthwise. So it's gonna read, and then strides. How many strides it's gonna move? It's gonna move 1, and padding is we're gonna keep it same. Let me explain what stride. So let's say this dropout. These are all pixel. Each alphabet counts as 1 pixel, and this is 1 dimensional. So when we talk about a picture, this would be a 2-dimensional pixels, right? So let's say I said my kernel size is 3. That means I'm gonna read 3 at a time in this 1-dimensional way. And then my stride is 1. So then I'm gonna move 1 pixel to the right. Then I'll read the next 3. Then again, I'll move 1 pixel to the right, and then read 3. So you keep doing it. If I put the stride 2, then I'll move 2 at a time. So now try to visualize this in a 2-dimensional ways. And when we say padding equal to same, we want to keep the number of pixels or number of outputs same as the inputs by adding some padding to it. So like, for example, let's say here, if I read 3 and give me 1 output. So let's say here I got 1, then I got another output 2, then 3, then 4, and then 5. So I reached to the end of this ladder schemes, but I have only 5. So I went from 7 ladder to 5 output. So you want to keep the output same. So by adding some padding, and that's what the padding same does. Okay. Now you're gonna act on this X. So I'm gonna add next layer would be my activation functions, and I'm gonna be adding to here, and then I'm gonna be adding a batch normalizations here. Let's say 90% momentum, and you're acting all of this on the previous layer X. Okay, let's copy this and repeat this a couple of times. Again, you can change any way you want. If you want to change to 16, that would be fine. But you could have done a for loop and change the stride to 2 maybe here. Again, it's something you have to play with it, what works the best for you. Okay, so now once you're done, so let's add another layer called flatten. And we're gonna flatten it out. And then next layer would be a dense layer, and units would be 128. Again, it's gonna work on X. So by putting X, we are asking it to work on the previous layers. Okay, and then add again an activation functions, and then add a dropout layer as well that will minimize. So we'll randomly choose 25% of the data to get to 0, so that will minimize our overfitting. You can choose any number you want. And the final is going to be our output layer. So that would be, again, another dense model. Again, this time the number of units is going to be 1. We just want simple output, how many colonies it has. Again, it's going to work on the previous layer. And the final step, let's call this Keras model. And it's going to be the model that we imported, Keras model, and it needs 2 things, input layer and output layer. All right, so hopefully we don't get any errors. You can check out how many parameters it has by looking at the summary. Okay, not too many. 1,135,425 parameters. Okay, it will take a while, about 30 to 40 minutes, depending upon the graphics card you have. If you're trying to do this with CPU, it's gonna take a very long time. So you might start in the morning and come back in the evening. Then probably it will be done by that time. So let's do this. So we have our Keras model ready to go. What we're going to do next is we will wrap this Keras model into a Deepchem model. Okay. So let's call a model. So this will be our Deepchem model. So it's going to be dc.models. And we're going to wrap this in Keras model. So we have to provide the actual Keras model name. So that would be the Keras model we just created right here. And then we have to provide the loss function as well, DC. And we're going to be using the L2 loss since it's kind of doing a regressions. Models.losses.L2 loss. And the batch size, how many samples you want to read at a time. So I'm going to do 1000. Again, it depends upon the how much memory you got. I could do a little bit more too, but let's keep it 1000. Okay, everything looks good. We are ready to fit model.fit, and we're going to be using our trend data sets, and number of epochs is going to be 50. So we're going to pass all of our data sets, all of the images 50 times. All right. Okay, so this will take about 30 minutes to 40 minutes. I will fast forward and cut directly into the output. Or maybe I will just do a second video, part 2 of the video. We shall see. All right, we are back. So it's done. Let's do our predictions. So let's define predictions equals to model.predict. And we're going to be predict on our test data sets. Let's print our predictions, first 5. So it will take a couple of seconds. So when it's doing that, you'll see it's printing out in decimals, while cell, like if you're counting something, it can be 82.95. So let's just round it up. So we can do this with numpy has rounding up functions. So predictions equals to np.rn. So it's going to get to the nearest integer. Let's reprint again. Predictions equals to, let's print predictions. That's what I meant. Okay, print predictions, and we're gonna print first 5 of them. So you can see it's rounded up to 83, 43, 93. So let's calculate root mean square error for our predictions. So so let's call it RMSC equals to so prediction minus test.y. So that's our error. So you want square. So now we want mean of it. So it's going to be np dot mean. Then we want square root of it. So I hope I have enough bracket. So again, we're going to do numpy square root. Okay, so let's see, our bracket seems good. Okay, predictions RMSC. Print root mean square. Oh no. Test data sets. There we go. Okay, so we got 41. So our actual model and test score is looking pretty good. 41. Let's do a plotting. How does the predictions and test data sets looks like? So let's do import matplotlib. Dot pyplot as plt, and let's import seaborn as SNS. Okay, so let's do figure axis, figure axis SNS PLT dot subplots, and we want the fixed size to be a little bit smaller. So let's do it 3 by 3, and axis equals to SNS dot scatter plot, and we want our x equals to, let's do predictions, and y equals to our test dot y. Oh, this is axis. All right, and ax equals to okay, ax, let's do set x label, so that would be x is our predictions, and ax dot set y label, and that would be our actual. Okay. Oh, one more thing. You can see this one here has a lot. Like this is a 1, 2. So this looks like a 2 dimensions. So this won't match. So we just have to add another things here. So it's gonna be prediction equals to prediction dot flatten. So we gotta flatten it up. Then it will be into 1 dimensions. Okay, you can see now. Okay, so now let's plot it. I'm keep doing the test ds. There we go. Okay, so it looks like it looks pretty good. So it's on this diagonal place. It's doing a pretty good job in predicting. However, there are a bunch of this over here. It doesn't look very good. So that's something to think about. I think the labels are not good if I think correctly. So let's try to maybe let's look at this one, 5. So this is 0, 1, 2, 3. So let's look at the sample number 5. So plt dot image show, and we're gonna see test datasets dot x. So that sample number is 0, 1, 2, 3. So it has 5. Let's see how does the actual pictures looks like. It will take a couple of seconds. Okay, 1, 2, 3, 4, 5, 6. Okay, 3, 4, 6, 7. It has 7 colonies. So maybe it's counting 1, 2, 3. This has 4, 5. So it didn't do a good job. Let's look at this one, maybe 62. That would be hard to count. That 62 is 4. So the image 4. Oh wow, that's very difficult to count, but it's getting close. This model, not perfect. All right, so this is how you do this convolutional neural network and use it in Deepchem. Like we used a Deepchem model to wrap the Keras model, and then we just use that for our analysis. All right, so stay tuned. It's been a long time I posted a video with all the classes and everything's got super busy. Stay tuned for more video. I'll try to post more video. I'll try to record more video this semester. So please stay tuned for anything's related to Deepchem, chemistry, biochemistry, and machine learning, all those related topics. Stay tuned.